Continuing along here, so I just want to keep going on describing our quantum mechanic operators. There's a lot of information here on what is a quantum mechanic operator, and they have these very obscure, bizarre mathematical properties. So I want to take some time on this lecture to describe this property that I have in front of me, and I'm going to do a rather large example problem after this. Okay? So all quantum mechanic operators that correspond to observables, such as energy or position, have a very special mathematical property. They are Hermitian. So a Hermitian operator is one that has hermiticity. I don't make up these words, I promise. And this is the mathematical property of hermiticity. Okay? So now you notice here that there's a little bit different of a qualifier on these wave functions that I'm using here, the subscript I or the subscript J. We're going to start to see some more and more of these qualifiers on our function notation. And so I and J refer to states. So let's write that down. I and J are states of our system. So for example, I could be the ground state. J could be an excited state. Okay, so that's what we use these I and J's for. So in the case of I and J being different, so here this is I and J not equal to each other. So again, perhaps I is a ground state, J is an excited state. Then hermiticity is the following. So we take the complex conjugate of the wave function of state I, okay? And then we have our operator that we are testing for hermiticity. And then this operator operates on this wave function first, okay? And so this is now not the complex conjugate, but it's just the wave function of state J, all right? And so in our order of mathematics, this operator would operate on psi J. Then we get a new wave function and corresponding eigenvalue, right? Then we take the square modulus of that result, okay? This operator will be Hermitian if then I can switch the order of that operation. And I just realized I drew over this little conjugate, okay? So this is Hermitian if now I switch the order of these wave functions. So now the operator will then operate on psi I, then we take the square modulus, okay? And it will be Hermitian if then I take the complex conjugate of that entire result. And if those things are equal, it is Hermitian, okay? So now we are only going to very rarely see this I not equal to J situation. What is much more likely is this case if I equals J. So in other words, we're talking about one state. Okay, so in this definition of hermiticity, I not equal to J, that would be two states, two different states. Okay, so if I is equal to J, right, we're really only talking about one state, so perhaps the ground state. Okay, and so now notice I no longer need to qualify the I's and the J's because we're saying it's the same state, same wave function. And now what ends up happening to this hermiticity property in the case of one state system, I equals J, we have the complex conjugate of the wave function, okay? The operator, and I like to call this operator sandwich because we've put the operator between the wave functions. So the operator operates on psi in that order, okay? Then we take the square modulus, all right? Now this one state system will, or the operator rather, will be Hermitian if now we switch the order of complex conjugates, right? And also we make the operator negative, okay? So this will still operate on this wave function, all right? And then we still take the square modulus. And if these two are equal, then our operator is Hermitian. Okay, beautiful. This is very difficult to understand just from this definition. So let's take a look at an example, okay? And I'm going to do some of this by hand, and I'm also going to confirm some of my results with, again, right? The operator operates on psi, and what we have to get back is a real number and the original wave function, okay? So the last thing I'll describe briefly is this orthogonal wave functions, and more on this notion of having different states, okay? So we've already talked about normalized wave functions, right? And if we set up the normalization condition, assuming here that these are already normalized, so I'll write psi I and psi j are normalized. And so if those wave functions are already normalized, and we're talking about one state, right, I equal to j, okay, then when I take the square modulus and integrate, I get that it equals 1. All right? Okay. So what about the case when I and j are not equal to each other? Okay. So this still condition applies. Psi I and psi j are normalized, right? But now in this case, when we're talking about maybe a ground state and an excited state, I not equal to j, then those wave functions have to be orthogonal, okay? So the interpretation of, and orthogonal means that when I take the square modulus of this, it's equal to 0. So the conceptual interpretation of these things are normalized wave function, there is a 100% chance of finding the particle within the same state. Okay? 100% chance of finding the particle, somewhere within that same state. Okay? And, somewhere meaning like, some distance along an x-axis, for example. Okay. The interpretation here is there is a 0% chance of finding a particle between states, okay? So in other words, if I have a ground state I, I'll represent this with our classic energy level diagram, and I have an excited state j, okay? When the wave function is normalized, if I suppose I make psi I and psi I, there's going to be a 100% chance I find the particle either in state I, or in the case that it's psi j, there'd be a 100% chance that I find the particle in state j. But what this orthogonality means is there's 0% chance that I find the particle somewhere between those two states, right? In other words, it has to be, either here or either here. Not in limbo somewhere between, okay? And this is one of the, origins of quantization or quantum mechanics. We can't find the particle between states. It's either going to be in state I or it's either going to be in state j.